Good afternoon, everyone. My name is Qingyang Wang. I was from Georgia Tech, but I just joined LSU as an assistant professor this year. Today, I'll talk about the lightning in the cloud, a study of very short bottlenecks on NTIA web application performance. This is a joint work with our industry collaborators, Fujitsu Labs in Tokyo. We all know that data centers are supposed to run at high utilization for high return on investment. But Gartner 2010 reports that servers in typical data centers are only utilized 18% on average, wasting a lot of resource and power. So why does this happen? Our previous research shows that SLA-sensitive applications suffer from wide response time fluctuations at relatively low utilization. And one important reason is very short bottlenecks. Very short bottlenecks are bottlenecks with very short lifespan, usually in terms of tens of milliseconds. For example, this figure shows the fine-grained CPU utilization of a web application server deployed in our data center, serving 8,000 users. The CPU utilization is measured at every 50 millisecond time window during a 20-second time period. And the average CPU utilization is just about 67%. And what's interesting here is that the CPU has very short saturations from time to time. And these very short saturations create very short bottlenecks in the system. As we found out that though bottlenecks are short-lived, these very short bottlenecks can cause large response time fluctuations for web applications, ranging from 10 milliseconds to 10 seconds, 3 orders of magnitude impact. For example, this figure shows our measurements of the polling time response time of the web application that deployed in our data center, serving 8,000 users. And the web application server, as I showed in the previous slide, is the most heavily utilized server in the system. So we can see that the polling time response time of the system has large fluctuations, even though the system is far from saturation. In fact, our statistical analysis shows that over 2% of the requests take longer than 2 seconds to finish, severely violating the quality of service requirement by most e-commerce web applications like eBay or Amazon. So the question here is, why are those very short bottlenecks can cause such large response time fluctuations? So in this talk, I show 3 causes of the very short bottlenecks that we found in different system layers. And for each cause, Java garbage collection in system software layer, and virtual machine consolidation in the application layer, and the CPU dynamic voltage and frequency scaling in the processor architecture layer. In each case, I'll show you step by step how a very short bottleneck can lead to requests with response time up to several seconds. I start by describing our data centers. This figure shows the 4-tier topology of the web application that we use in our experiments. We use Apache as web server, Tomcat as application servers, CJDBC as a load balancer for the database tier, and MySQL as database servers. We use the Rubos, a well-known web application benchmark based on a bulletin board system modeled after Slashdot. The workload generator of this benchmark emulates a certain number of users interacting with the web application. Each user has an average 7-second thinking time between receiving a web page and submitting a new page download request. And the workload of this benchmark can be CPU intensive or mix of CPU and I/O. And we use the CPU intensive workload for this paper. The machine we use in this paper has 2 quad-core CPU with 16 gig memory. We also use a passive message timestamping infrastructure in our experiments. The passive message timestamping infrastructure sits with router box. So this router box is a specialized network switch from our industry collaborators, Fujitsu Labs in Tokyo. So all the servers are connected to the sit with router box in our experiments. So any interaction messages between any two servers needs to go through the router box. In this case, the router box is able to record the precise arrival and departure timestamps of every request for any server in the system, as shown by the figure on the right. Basically, with the precise arrival and departure timestamps, we have the exact knowledge of each request processing at each tier boundary. So, for example, we know the precise response time and the number of queued requests in each tier. Here is our measurements of the 3 minutes benchmark on the 4-tier web application that with increased workload. The figure on the left shows the average system response time as we increase the workload from 1,000 users to 17,000 users. And the figure on the right shows the average system throughput at each workload. And we can see that at workload 9,000 users, the average system response time is just about 80 milliseconds, which is pretty low. And the throughput at this workload hasn't reached to the maximum yet, which indicating that the system is not saturated. In fact, at this workload, the average CPU utilization of the bottleneck server is just about 61% utilized, far from saturation. So at workload 9,000 users, the average system response time is pretty low. But how about the polling time, response time of the system? The figure on the left shows the polling time, response time of the system during a 20-second time period. So we can see large fluctuations, even though the average system response time is just about 80 milliseconds, which is not representative of the real system performance at all. The figure on the right shows the response time histogram of all the finished requests during experiments. The x-axis is the response time, and the y-axis is the frequency, which means that how many requests are finished with certain response time during the experiments. The y-axis is in log scale. And we can see a clear bimodal distribution of the response time. Even though the average system response time is just about 80 milliseconds, the number of requests take longer than 2 seconds to finish are over 2%. So such high percentage of long requests severely violate the quality of service requirement. Next, I'll show that both the large response time fluctuations and the requests with very long response time are due to very short bottlenecks caused by the Java garbage connection in the Tomcat tier. The figure on the top shows the Java garbage connection activities of the 2 Tomcat servers during a 20-second time period. The x-axis is the time, and the y-axis is the Java garbage connection running ratio. So we can see that both Tomcat 1 and Tomcat 2 have frequent Java garbage connection activities. The figure on the bottom shows the fine-grained CPU utilization of the same 2 Tomcat servers during the same 20-second time period. And we can see that once there's a Java garbage connection happens in a Tomcat server, the corresponding CPU is 100% utilized. And this occurs because we use the JDK 1.5 in Tomcat, which uses a stop-the-word Java garbage collector. What this means is that when Tomcat needs to clean garbage in memory, it will consume 100% of the CPU for 50 to 100 milliseconds. And these very short CPU saturations create very short bottlenecks in the system. The figure on the top shows the fine-grained CPU utilization of the same two Tomcat servers from the previous slide. Let's see how these very short CPU saturations affect the CUDA request in the system. The figure on the bottom shows the number of CUDA requests in both the Tomcat tier and the Apache tier. The pink line is the Tomcat queue, and the blue line is the Apache queue. So we can see that whenever there's a transient CPU saturation, as shown in the top figure, there's high peaks of the CUDA request in both the Tomcat tier and also the upstream Apache. So it is not a stretch to suggest that a very short bottleneck in a Tomcat actually causes request to queue in its own server. But can we also conclude that the same bottleneck in Tomcat also causes a large number of requests to queue in Apache? The answer is yes, and we can. And I explain how this happens in the next few slides. The figure on the top shows the Apache queue from the previous slide. And the figure on the bottom shows the polling time response time of the system during the same 20-second time period. We can see that the peaks of the Apache queue also match well with the peaks of the polling time response time of the system, indicating that the peaks of the system response time is caused by the CUDA request in Apache. Long queue in Apache also causes requests with very long response time. The figure on the top still shows the Apache queue from the previous slide. The figure on the bottom shows the number of requests with response time longer than 3 seconds. And this is monitored at every 50 millisecond time window during the same 20-second time period. And we can see that the peaks of the Apache queue also match well with the happening of the large number of long requests. This occurs because every Apache server has limited number of threads to process the concurrent requests in the server. The underlying operating system TCP stack also has a buffer for CUDA requests called backlog. And so the maximum number of requests that can be queued in the Apache server is the number of threads in the Apache server plus the operating system TCP stack buffer size, which is 278 in total. So what this means is that once the CUDA request in Apache exceeds such concurrency limit, the new coming request will be dropped, and TCP retransmission happens. The current TCP retransmission protocol requires that the client side to back off at least 3 seconds to resend the request, causing requests with a very long response time. Next, I'll explain that how a very short bottleneck in Tomcat also causes large number of requests to queue in upstream Apache. Here is a simple illustration. At T1 time marker, and requests start to queue in Apache due to a very short bottleneck caused by Java garbage connection, for example. And Tomcat queue soon fills up, causing Tomcat to block new requests. In this case, the new coming requests are forced to push back to the upstream Apache. What's more interesting here is that all kinds of requests start to queue in Apache, even though some of them has nothing to do with the very short bottleneck in Tomcat. For example, the purple boxes, some requests ask for only ask for the static images, as shown by the purple boxes here, are only served by the Apache server and never go to the Tomcat server. But due to the pushback of the request from the Tomcat server, these requests are also needs to queue in Apache. In this case, the queuing effect in the Apache server is amplified, and I call this phenomenon as the pushback wave. the entire pushback wave can be very fast. In fact, can happen within 100 milliseconds. But the performance impact is huge. In this set of experiments, I showed that very short bottlenecks can cause large response time fluctuations. And the reason is because of the pushback wave caused by the complex resource dependencies in the system. In fact, the very short bottleneck caused by the Java garbage collection in this case can be fixed by upgrading the JDK version from 1.5 to 1.6 or 1.7. This is because the newer version of JDK uses much more efficient garbage collector. But some very short bottlenecks are not easy to fix, especially when the workload for web applications becomes bursty. Web applications are well known to have a bursty workload. This means that the workload fluctuates frequently between the low and high request rate. For example, this figure shows a sample workload trace of the sample workload trace for the web application deployed in our data center, serving 8,000 users. We can see that the request rate fluctuates frequently if we monitored at every 50 millisecond time window. So we found that the virtual machine consolidation can cause hard-to-fix very short bottlenecks when the workload for the web application becomes bursty. Consolidating VMs is a very common strategy for cloud vendors to increase the hardware resource utilization and maximize profit. The state-of-the-art approach is to consolidate multiple underutilized servers into the same physical machine and let them share using the beam packing algorithm. The problem is there's a potential performance interference among VMs sharing the same hardware resources, especially for VMs hosting web applications. This is because web applications naturally have bursty workload, which means that the VMs, the resource demand by VMs can vary significantly. The high resource demand of one VM can limit the available resource for the other collocated VMs, causing severe performance interference. And we call this phenomenon as the noisy neighbors. Next, I'll show our consolidation strategy of two web applications. The first system still uses a 4-tier topology as I used in the first case study. And I call this system as a Sys-Original. The second system uses a simple 1-1-1 configuration, one Apache server, one Tomcat, and one MySQL. And I call this system Bursty. At the beginning, Sys-Original serves 14,000 users, and Bursty serves 400 users. Bursty means that the users interacting with the web application are not independent. Some of them are correlated with each other and send a request to the web application at the same time. So in this case, the peak request rate can be much higher than the average. Such bursty workload is also very common in real world and well known as the /dot effect. We use an open source workload generator to emulate 400 correlated users for system bursty. At the beginning, each server is running on top of a VM deployed into a dedicated physical machine. And the Sys-Original Tomcat 2 is CPU utilization is just about 74%, and 10% for Bursty MySQL. So based on the beam packing algorithm, we consolidate these two servers into the same physical machine and let them share the same CPU core. The figure on the left shows the point time response time of the Sys-Original during a 15-second time period. We can see large fluctuations, even though the average system response time is just about 90 milliseconds, which is not representative of the real system performance at all. The figure on the right shows the response time histogram of all the finished requests of System-Original during the experiment. So we can see a clear long tail and a bimodal distribution, as we have already seen in the first case study. Next, I'll show that both the large response time fluctuations and the request with very long response time are due to very short bottlenecks caused by the interference among collocated VMs. The figure on the top shows the polling time request rate for system bursting during a 15-second time period. We can see frequent peaks of the request rate for system bursting. For system bursting request rate, let's see how these peaks of the request rate for system bursting affect the performance of the collocated System-Original. The figure on the bottom shows the fine-grained throughput of the System-Original during the same 15-second time period. And we can see that the peaks of the request rate for system bursting has a strong positive correlation with the short-term throughput drop of System-Original, indicating severe performance interference here. The figure on the top still shows the point time request rate for system bursting. And the figure on the bottom shows the fine-grained CPU utilization of System-Original Tomcat 2, the collocated server with the system bursting MySQL. So we can see that the peaks of the request rate for system bursting also match well with a very short CPU saturations of System-Original Tomcat 2. This happens because the peak of the request rate for system bursting causes the short-term high demand of the CPU resources by the system bursting MySQL. So the System-Original Tomcat 2 perceives 100% of the CPU utilization due to the shortage of the shared CPU resources. The figure on the top shows the fine-grained CPU utilization of the System-Original Tomcat 2. Let's see how these very short CPU saturations affect the queued request in the system. The figure on the bottom shows the number of queued requests in the System-Original Tomcat tier and also Apache tier. And the pink line is the Tomcat queue, and the blue line is the Apache queue. We can see that the very short CPU saturations as shown in the top figure causes a large number of requests to queue in the Tomcat tier and also the upstream tiers due to the pushback wave. The following analyses are similar to our first case study. Long queue in Apache causes large response time fluctuations and also requests with very long response time. The figure on the top shows Apache queue and the point time response time. And the figure on the bottom shows the Apache queue and the happening of the large number of requests with very long response time. So we can see that the long queue, the peaks of the Apache queue also match well with the peaks of the system response time and also the happening of the large number of requests with very long response time. The reason is the same as the first case study. Basically, the pushback wave basically amplifies the queuing effect from the source to the upstream tiers. And once the queued requests in the upstream tiers are full, the requests start to drop and TCP retransmission happens. And the third case is the very short bottleneck is caused by the dynamic voltage and frequency scaling. Basically, DVFS, this CPU DVFS case. CPU DVFS is designed to handle bursty workload to achieve both good performance and power saving. And a DVFS controller is able to adjust the CPU frequency and the voltage based on the real-time workload. But the problem is, since the workload burst length for web applications can be close to the DVFS control period, there's a potential of anti-synchrony between the CPU DVFS adaptation period and the workload burst length. And such anti-synchrony causes very short bottlenecks in the system. And due to the time constraints, basically, I will not introduce this case in details. The principles are the same as the first two case studies. I'll go through this quickly. We observed basically the large response time fluctuation and requests with very long response time. And then I showed that the delay of DVFS adjustment creates the very short bottlenecks in the system. And the very short bottlenecks cause the queue to build up in the bottleneck tier and also the upstream tiers due to the pushback wave. And the queued request causes large response time fluctuations and also requests with a very long response time. So, conclusion, in this talk, I have introduced 3 causes of very short bottlenecks in different system layers, which means that very short bottlenecks are very common in real systems. And the most interesting message I want to show here in this talk is, though very short bottlenecks are short-lived, they can have a very big impact on web application performance. The reason is because of the pushback wave caused by the complex resource dependencies in the system. Due to the pushback wave, the queuing effect from the bottleneck tier can be amplified to the upstream tiers and eventually lead to dropped requests and TCP retransmissions. Any questions? Thank you.
So you've identified a lot of interesting problems there, but you didn't propose a solution. So what do you think we should do about these pushback waves?
Yeah, that's a very good question. You mean basically the solution for very short bottlenecks is there are 2 kinds of solutions. So basically, one is the solution for each cause of the transient bottleneck. We may propose solutions to cure the cause, like the Java garbage connection case. We kind of solve it by upgrading the JDK version to a higher version number. And for the VM consolidation case, in fact, we really don't have a good solution for that. And what we can do is to kind of, if we detect those noisy neighbors, we probably need to migrate the VM to a different physical machine. And of course, to develop general solutions for this problem is we are working on that. Basically, we are thinking about ways to kind of to break the pushback wave in the system, but it's still ongoing.
Other questions? Yeah, I have one question. So even apart from solving it, it seems like diagnosing these problems is really difficult.
Yes.
You have to know something about the internal state of some process. So do you have any insights having diagnosed a handful of these problems? How to have a general diagnosis system so you can kind of figure out if they perceive latency spike, figure out and then figure out the root cause of those spikes?
Yes, very good question. Basically, to diagnosing the cause is indeed it's not easy. How can I say? Now, what I can say is that just apply the fine-grained monitoring tools you have, just to apply to monitor to collect as much data as you can at fine granularity, and yeah, basically the more powerful of your the monitoring tool is, the more capable for us to detect those very short bottlenecks. And there's no basically general solution to detect those the exact root cause for that.
Okay, fair enough.